This is a series of tutorials in my Fundamentals of Anesthesiology series on the core topic of gases. First up, we're going to talk about the forgotten gas, and that is water and the saturated vapor pressure. An introduction to anesthesiology with me, your host, Pat Nelligan. Understanding gases and vapors, Part 1, Saturated Vapor Pressure. I'm walking through the ICU, and one of the patients who is mechanically ventilated has a very strange jingle-jangle waveform on their vent screen. On closer inspection, the expiratory tubing is full of water. Why? One of the first things one learns in science as a child is that all matter can exist in three forms: solid, liquid, and gas. They can also coexist in those forms simultaneously. Water is the most ubiquitous substance that we encounter in different states. It exists as ice, water, and steam, but we also encounter water vapor. What is the difference between a gas and a vapor? Well, this is mostly about terminology. We use the term gas to describe a substance that exists as a gas under normal conditions. That's room temperature, or the temperature in which we live, and the pressure in which we live. Hence, oxygen, carbon dioxide, and nitrous oxide are gases. A vapor is a substance that is usually liquid under normal conditions, but gas escapes from that liquid at that temperature and continues to do so until the liquid boils and the substance becomes a gas. Examples of this are water and all of the volatile anesthetic agents that we use: isoflurane, enflurane, desflurane. Everybody in the world is familiar with the concept of melting. At the melting point, if ice is left in position at constant temperature of 0 degrees, it will eventually completely liquefy. So it's the state in which a substance changes from solid to liquid, and the solid and liquid phases exist in equilibrium, and that's 0 degrees Celsius for water. As the liquid heats, gas molecules are released into the surrounding space. The quantity of gas directly relates to the temperature. This applies a pressure on the surface of the liquid, the saturated vapor pressure. And for all temperatures where gas and liquid coexist, there is thermodynamic equilibrium. The rate of release of molecules to gas equals the rate of return to liquid. For water, in colloquial terms, the rate of evaporation equals the rate of condensation. At 20 degrees Celsius, the saturated vapor pressure of water is 2.3 kilopascals, or 20 millimeters of mercury. At 60 degrees Celsius, the saturated vapor pressure is 20 kilopascals, or 150 millimeters of mercury. In the real world, warm air holds more water than cold air. That's why humidity increases with temperature. It's also why your breath condenses in cold air or onto colder surfaces, such as when you blow on your eyeglasses to clean them. With water and other liquids, the saturated vapor pressure increases progressively as the temperature rises. At 100 degrees Celsius, the saturated vapor pressure is 101 kilopascals, or 760 millimeters of mercury. At this point, the saturated vapor pressure exceeds the atmospheric pressure. That is why we see bubbles. At boiling point, gas is released throughout the liquid, not just from the surface. But be aware that with water, bubbles appear below the boiling point emerging from the liquid. That is not water vapor, it is air that's being released from the water. These are the little bubbles that you see coming out of crystalloid in intravenous fluid tubing after it leaves a fluid warmer. At sea level, the boiling point is 100 degrees Celsius, but as one ascends, water will boil at a lower temperature. If you look at anesthetic gases and anesthetic vapors, they all have different boiling points. For example, nitrous oxide has a boiling point of minus 88 degrees Celsius. What does that mean? It means that nitrous oxide exists only as a gas as we know it. Isoflurane, sevoflurane, and methoxyflurane all have boiling points that are significantly higher than the temperature that we normally see on the face of the earth. For isoflurane, it's 48 degrees Celsius. Sevoflurane, it's 58 degrees Celsius. Methoxyflurane, it's more than 100 degrees Celsius. Desflurane is a little bit different because its boiling point is near room temperature. We will discuss that at a later stage. A typical vape that you might buy in a dodgy mobile phone shop requires 200 degrees Celsius to boil, so it needs to be heated by a little battery to vaporize. Hence, if you look at volatile anesthetic agents, they come in bottles that contain liquids. For sevoflurane and isoflurane, you can take the lid off the bottle and it'll stay liquid for a period of time. It eventually all evaporates off. Methoxyflurane, on the other hand, is very stable. And as a consequence of its stability and the fact that it just doesn't vaporize off that easily, it is now used as a portable device for giving a sedative to patients who may have severe pain involving trauma. And you'll often see patients coming into the emergency room sucking in on these devices. This particular device is known as Pentrox. So here we have water, and above water we have water vapor. That water vapor applies a saturated vapor pressure to the surface of the water. Our bodies are made up 60% of water, and there is a water-air interface in the body in the lungs. At 37 degrees Celsius, the saturated vapor pressure of water is 6.3 kilopascals or 47 millimeters of mercury. And this is really important. As air is inhaled from the outside and passes down the airway, it is progressively hydrated with water. And by the time that air arrives in the alveolus, it is fully saturated with water. The alveolar water vapor pressure is 6.3 kilopascals or 47 millimeters of mercury. When you put a patient to sleep and you insert an endotracheal tube, cold air goes in and passes down the airway, avoiding all that humidification along the way, and dry air is sent down into the lower parts of the lungs. And subsequently, very warm, moist air leaves the patient. This will rapidly lead to dehydration of the patient, free water loss from the patient, but also the mucous membranes start to dry up and the mucus cakes up and starts plugging up the lungs. Dehydration and mucus plugging is prevented by humidification of the breathing system. In the ICU, we use a sophisticated humidifier that is placed in line in the inspiratory limb of the breathing circuit. In the operating room and in the emergency room and in transport situations, we use a simpler device. It's known as a heat and moisture exchanger. Some things to consider. Water condenses in cold circuits, so watch out for water in your breathing system, particularly in the ICU. That's what was happening with my patient in the ICU. The expiratory limb of the breathing circuit was filling up with water. High flow oxygen delivery systems heat the inspiratory tubing to prevent water from condensing in it. Otherwise, the patient will be power washed with the nasal catheters. If used, for example, in the ICU, the heat and moisture exchanger should be changed every 24 hours for two reasons. One, they get just completely full of water, and two, the bacterial part of the filter fails. So this is the heat and moisture exchanger, and it connects into the anesthetic machine by this side stream analyzer tubing. Just below where the tubing connects, water can condense and get caught by a water trap. But this rarely fills, and there's a good reason for this. This is how the HME, the heat and moisture exchanger, works. The yellow part is made of a material that traps water. The simplest material is cardboard. The red part is a moisture barrier and a filter that traps bacteria. When gas flows out of the lungs, water vapor is carried in it, but when the water encounters the HME, it gets trapped there. When the next breath arrives, the dry gas encounters the HME and picks up the trapped moisture, just delivering the moisture to the patient. It's a really efficient system. So condensation usually occurs on the expiratory limb of the breathing circuit. That's what was going on with the patient in the ICU. The tubing was filling with water. Sometimes you just have to disconnect it and pour the water out. It rarely occurs in the operating room because of the efficiency of the HME. But if the HME fails, for example, it's cracked or damaged or broken, the water trap in the anesthetic machine fills with condensation, and eventually an alarm goes off to warn you about this. Let's review this tutorial. In this tutorial, we looked at phases of matter, gases versus vapors, saturated vapor pressure, boiling points, and airway humidification and condensation. Next time, we'll talk about the gas laws. I'll see you then.